Hello, this is a quick tutorial for EEC119 mixed signal senior digital, senior design. Anyways, the circuit that you see in front of you is known as a constant GM cell. You can find this in Razavi on page 373. I have a reference right here. So the basic principle, let's ignore this purple NMOS right now, this diode connected NMOS for a sec. The way this circuit works, it's for basically setting up a bias current that's relatively independent of supply voltage. So if you have a current that's going through this PMOS here, it'll be, these PMOSs, if you notice, are the same size. So to the first order, it will the current on this side will be equal. So what you do is you don't set the NMOS equal to each other. Well, this is one way of doing it. You don't set the NMOS equal to each other, and you put a resistor down here. Now, one thing is there is the body effect here because it's connected to ground. If you make the mirror of this and use a PMOS, you can connect it directly. You can in the PMOS case, you can isolate it in its own well and connect the body to the source. So if you notice, I assumed that there's no body effect. I assumed gamma was equal to 0. So if I assume that gamma is equal to 0, the threshold voltages cancel out. But to the first order, this will get you pretty close. So anyways, what's happening is that you're using this resistor and this cell here to basically set a current that's independent, relatively independent of supply to a point. And this, the way that you solve for that is you have a voltage rise of VGS here, you have a voltage drop of VGS, and another voltage drop here due to the current going through the resistor. And basically you fill in you fill in for saturation and current there, and you solve for I. And for example, like an I of 10 microamps in the 180 nanometer technology process that we're using, with a W over L of 5, I picked a 10 kilo ohm resistor and a K of 10. So I have 10 of, yeah, I think I put 10. Or I'll show you guys in a sec. But I have 10 here, 1 there, multiples wise. But this is these guys have a ratio of 5 to 1. Okay, so I'm gonna show you guys a little simulation. So anyways, this is the formula right here that will govern what's going on with the currents here. Once again, this purple circuit is so that you have a DC path at startup, because this circuit is stable as being completely off or completely on. So, so here I have a simulation up and running. So what I did here is this is my op-amp. I have a load cap here of 50 picofarads. I have a feedback. Basically I'm doing a unity gain. This guy right here is for stability analysis, so there's no voltage drop across this guy. Oops, wrong thing. So I have 0 DC drop across here. I do have an AC signal, 1 volt AC signal for AC simulations, though I don't think you need that with the stability analysis, but I haven't changed it. And I have 1.8 volts supplied to this guy. Right now I am showing the DC operating points, and I'll show you how to get that in one sec. So really quick, zooming into this constant GM cell, let me show you the parameters. So if you go to Results, Annotate Component Parameters, you can see the devices that I use, the widths, the links, the multiples. So these two are equal. I made this device really long. The reason you want to make this device really long is when this is turned on, you want this to consume very little current. So I made this guy a very long channel device, and I didn't make it very wide, as you can see. This devices are equal except I have a multiple of 5. Oh, so I used a multiple of 5, and I guess I used a ratio of 5 too. And you can ignore this circuit for now. I'm trying to add additional current to improve the the gain a little bit, matching. But anyways, what I have here is the PMOS. I'm generating a current reference here, and that's being used to bias this current mirror, this current mirror, and this current mirror, so that I get my approximate 10 microamps. Except this is multiple 2, so I'm getting 20 microamps and splitting it. And then these guys are half the width, and then I have a multiple 2. I could have split those, but I was just messing around differently. Anyways, let me show you a couple simulations and how to set them up really quick. So I'm going to delete these, and okay, so first, remember you need to choose your model libraries and all that stuff. If you don't remember, you need it's in /projects NCU blah 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 /models spectra blah blah blah. Press OK. Analysis choose. We want transient analysis, just in case we want to look at how the waveforms are doing time-wise. Choose conservative. Options. I tend to like to choose Euler algorithm under algorithm. So press OK. Press OK. Analysis choose. We want the DC operating points, so save DC operating point. Press OK. And then analysis choose. We need stability. Now for the stability, you need to give it a frequency sweep. And what you do, the next thing is you need to choose a probe instance, and that's where I put this voltage source here. So once I click on that, it says V3, which that's the voltage source. Press OK. So I'm going to save my setup. Press OK. Oh, and I'll show you how to get these down here in a sec, but let's delete these for now. So when I run it, I won't see anything being plotted. But what we can do is we go to results. Oh, hold on a sec. Let's zoom in around here, around the OPAMP. And let's go results, direct plot. Results, annotate. You want DC node voltages. You want results, annotate DC operating points. And so this way you can tell if something's very quickly in saturation, linear, or cutoff. These two devices I'm kind of cheating. I'm using them in cutoff to get a little bit of extra gain. But the rest of the devices are in saturation. So remember, for saturation, VGS has to be greater than your threshold voltage. So in this case it is. But VDS has to be greater than VGS minus your threshold for saturation. So if you look right here, my VGS is 0.3 and my threshold is 0.4. So this guy is slightly in cutoff, but that's okay. For what I'm doing here. You guys will probably more likely want to get this in saturation, but you can use these in cutoff. What I'm doing here is I'm trying to match these voltages better, so I'm actually bleeding off a little bit of current into here, so the currents will match between these guys a little bit. So I'm using this reference point to set, basically I generated another, this is a current mirror here, this voltage is fed back into here, and then I'm feeding from my original current reference a current here, so some current goes into there. So let me show you the stability analysis. So if we go results, because I just ran this, direct plot, main form, and we you can choose transient or stability. Choose stability. And so the nice thing is if you click on phase margin, it'll tell you what your phase margin is. So right now I'm running this with, so you want a phase margin of at least 45 degrees. 60 degrees is better. You'll get a little bit of ringing with 45 degrees. So I'm going to change this load cap right here. You should run your simulations with some sort of load, but I'm going to show you, oops, that's huge. I'm going to show you that that the stability changes when I run a new simulation. So if I go results, direct plot, main form, phase margin, see it dropped a bit, 53. That's still pretty good. So I'm going to put this back at 50. Oh, actually it doesn't matter for the rest of the demonstration. Okay, so now if we go results, results direct parat main form, you also can choose the phase margin frequency, so this will tell you at what frequency it crosses. Or what you can do is you can go loop gain, choose magnitude and phase, dB20, and choose select add to plots, which will put this down to here, say plot. See how it popped up here? Let's go ahead and save that state. And what you'll see right here is this is my phase and this is my gain. So another way that you can measure your phase margin is you put a trace marker right there, and what we'll do is we'll edit this. We'll move it by Y, and we will move it to 0 dB, and so about 14.6. So that is 52 degrees phase margin, which is stable. So anyways, this is how you do stability